and angle from minus infinity to plus infinity. And a single leader. And now, so that the signal is not just one number, but a sequence of numbers. And that is, for example, I put the microphone outside the window recording the noise for every 5 seconds, for example. Another 5 seconds, again, another tip. So they all even value. Now let's say collecting enough of them, and they keep changing. So every sample is one random variable. And a collection of these things here, I have a random signal, but sometimes we call this a random process. So now you imagine, right? So now not just one random variable, but many of those. So for that, is a random signal or sometimes called a process if its sample xn is a random variable. Okay. So you see, I have a random variable. I need to use the probability density function to describe it. But now, if I have many random variables, I need to describe it using a joint distribution or joint density function. Right? Joint. So that leads to something. So, for example, so this requires. And it requires the specification of the probability function. So now with the slightly the probability density function of not just one single sample, but now I use a random variable x of n1, x of n2, at least I need to have the probability density function of small x of n1, x of n2. And then inside it's n1. So that means I have to describe the joint distribution function for each random variable and its label and its any collection of them. Right? I have to describe them. A complete description of the signal is required. Now that turned out to be a little bit too much. Right? Too much to describe. And again here, as an engineer, we need to describe the word as precise as we can, but as simple as possible so that we can derive some effective algorithm. Okay. So now we're going to introduce a concept that going to now make the thing simpler. Simpler in the sense that it requires fewer parameters so that we can program and use it effectively in a computer. Okay. So, but let me ask, who has seen random variables before in this class? Okay. It's about who has seen the random process? Okay, so this thing is familiar to half of you, right? The other half is, can you see this? People who learn this know that this little bit changed at first, right? Because we like everything to be fixed, right? I tell you a number, that's it, take that number. But now having a sample and a random description of them is a little bit difficult to deal with first, conceptually. But I hope by going through this, some of the simple example, and again, you have a chance to do the homework, it becomes slowly, familiar to each of you. And trust me, it is a very important concept for engineers in signal processing and communication and many other areas. Okay, so the word questions. And as bonus for that, the second part of today's lecture, I will show you how this is going to be used in a very advanced and powerful tool of signal processing called adaptive filtering. Okay. Alright, so we're going back here. This is about too much description for a random signal of processes. Because I have to describe all of this, so I have to describe the whole. So sometimes in signal processing, people can assume, so this is quite common assumptions. It is, you have to make some assumption. You have to make some assumption about the problem. You make the thing simpler to deal with. And you want to make the assumption that at least realistic. Okay. So any assumption you put in, make the thing narrower, but you hope that it's still rich enough to capture the thing that we want to deal with. Okay. So one of the assumptions we add on here is a stationary processes. Okay. So I don't know why, but there's pretty good the historical reasons. In the random world, a random signal is a random process, right? So stationary processes tell you a stationary signal. So we can use this term, two-term interchangeably. Okay? Okay. So a stationary process is when the definition here is, simply put, a stationary process. I have a signal, which every instant of time I have some random variable, and it has some statistical property, right? And the statistical property is precisely defined by the joint density function. So the stationary process is that this signal starts from very beginning and keep going here. What we say here is statistical property doesn't change with time. It's stationary. That's what I see. So I have some noise, and the noise here is random. You have some stochastic statistical property, but these properties keep the same, doesn't change with time. It doesn't. Okay, right? So it's to be more precise, we have to put a capital H in the random variable. But again, signal processor, we get used to it. We know what we talk about. So let's say X and is a stationary random process if I have probability of X and 1 X and capital N1 to N come here, for example. I have this joint density description of this N sample. So I take the signal, let's say I do some